Hi all. In module 1, that is key enablers for LTE features. Today we can discuss about the broadband, that is modeling broadband wireless channel. Already we have discussed about this broadband wireless channel is categorized into two: statistical channel method as well as the empirical channel method. Let us have a discussion about the statistical channel methods. As we know that we are transmitting a signal from the transmitter to the receiver. So how this effectiveness of the signal will be measured? For this purpose, we are going for the modeling. There are two major classes of models, that is statistical models as well as the empirical models. And if you come to the statistical model, it will be used for analysis and simulations. And if you come for the empirical models, that is nothing but that will represent the specific type of channel which can be achieved more accurately. Then this will let us go an in-depth explanation of the statistical models. Okay. And this statistical models is going to characterize the signal into two categories. One is the amplitude of the signal and another one is the power of a received signal. So the power of a received signal is represented by R of t. Okay. And here these two categories are taking into accountable when all the reflections arrive about the same time. Okay. And also we know there is a delay spread. We have studied about the delay spread, coherence, bandwidth, Doppler spread, all those things. Here we are considering the delay spread, that is capital T is very greater than tau max. Okay. And these models are often called as narrow band fading channels. And there are three types of popular statistical models are there. That is nothing but Rayleigh Fading, Gaussian distribution, and Nakagami F fading. So this how we are going to characterize the three types of fadings. Let us discuss one by one. First we will see the Rayleigh fading. Okay. And in this Rayleigh fading, actually many objects in the environment which will scatter our radio signal before it arrives at the receiver. Okay. And here we are using the theorem called central limit theorem. Okay. And this theorem is used in such a way that the channel impulse response will be well modeled in respective with the Gaussian process of the distribution of individual component. So here we told that the objects are going to scatter the radio signal. Okay, already we know that while transmitting a signal from transmitter to the receiver, there are multi-path. That is only line of sight is that is but direct path, and through the obstacles and through the multi-path transmission in the last session we have discussed. Okay, so here we are going to give some statistical measurements by considering the envelope of the channel response. Okay, that is Rayleigh distributed. Here we will see the received signal. The received signal is represented by R of t, and the time is at t is equal to 0, and R of 0, that is R I of 0 plus R Q of 0. We know that whenever we are going to take the account of the power signal, there is two components, that is in phase component and the quadrature component. So here Ri of 0 is in phase component and Rq of 0 is quadrature component. So that is Ri of t and Rq of t, but we consider that time t is equal to 0. Okay. So this are in terms of Gaussian random variables. Now the envelope, that is nothing but amplitude, the distribution of the envelope amplitude, that we are represented by modulus of R. So that can be written as square root of R squared I plus R squared Q. That is the Rayleigh, and the received power can be represented, that is exponentially distributed. For that we will write the formula, that is F suffix modulus R of x is equal to 2x divided by PR into e power minus x squared by PR. under the condition x greater than or equal to 0. The same way for f modulus of r the whole squared of x, that we can done as 1 divided by pr e power minus x by pr, that is also under the condition x greater than or equal to 0. Now coming to the path loss and shadowing. In the last session, we discussed about the path loss and shadowing is not a fading, but it is a factor which creates it is a fading. So these two parameters, path loss and shadowing, can determine the mean received power and also the total power received power fluctuates around this mean due to the fading. So this graphical representation is given a clear picture that in the y-axis we have marked as received power in terms of dBm, and in the x-axis it is d. So here we can see, including the fading around shadowing plus path loss, what is the amplitude of the signal. So only the path loss, what is happening. So in there it has been mentioned with the dark line as well as the sinusoidal wave. So but from this diagram it is very clear how the envelope is going to be distributed in the Rayleigh fading. The next we will see Rayleigh distribution. So Rayleigh is that when we come to know the arriving reflections have a mean of 0. Now coming to the Rayleigh fading, it is line of sight path, that is LOS, line of sight path between the transmitter and the receiver. So for a line of sight signal, the envelope, the received envelope distribution is more accurately modeled by a Rayleigh distribution, and the formula has been given by x by sigma squared. Actually here we are taking it as a factor actually under the condition of x greater than or equal to 0, and we are very clear that Rayleigh distribution depends on the line of sight component power, that is mu squared. Okay, and how there is a common way how we are going to characterize the channel, that is only by the relative strength of the line of sight and the scattered path. For that, the fact we are using a quantified factor that is called as k. So k is equal to mu square divided by 2 into sigma squared. So this is the way the distribution of the signal is going to be happen, and the channel will be characterized with the two parameters. One is relative strength of the line of sight and the scattered path. Next we will come to the Nakagami M fading. Okay, actually this fading is nothing but general model for wireless channel. Here we will use the probability density function, that is PDF, to parameterized by M and given us. So the formula is given as such a way in terms of M, and under the condition M is greater than or equal to 0.5. So here whenever we are using this Nakagami distribution, there is a tractable analysis, okay, for fading channel performance. In the fading itself, we have discussed about short-term fading, long-term fading, and if you come to that the wireless cellular concept, there is adjacent channel interference, co-channel interference, as well as the other channel interference. So keeping all those things in the mind, narrow band fading, broadband fading, we are going for the modeling. Modeling is to analysis the thing by using some parameters. So here, whenever coming to the Nakagami distribution, the power distribution for the Nakagami fading is mathematically expressed like f modulus r of squared of x is equal to m divided by pr the whole power m into x power m minus 1 divided by gamma of m into e power minus mx by pr. So the parameter m should be greater than or equal to 0.5. So under the statistical channel methods, we have discussed about the Rayleigh channel fading and Rayleigh fading and Nakagami fading. So among this, we have taken some envelope, that is amplitude, then power of the signal. We are distributing in the form of Gaussian process. Then we are going to introduce some parameter under the condition, and we are going to calculate the channel statistics, channel methods. Now coming to this analysis of statistical correlation of received signal in different domain, there is time correlation, frequency correlation, dispersion, selective, duality, multidimensional correlation. These are the received signal in different domains. Okay, so each domains will have different parameters and different statistical levels and different graphical representation. So if you come to this statistical channel methods, we are very clear with three different types, that is Rayleigh, Bayesian and Nakagami. And received signal is also having different domains, that is time correlation, frequency correlation, dispersion, selective, duality, multidimensional correlation. Then coming to the time correlation, in the time domain, the x-axis we have taken it as time delay, and the y-axis it is the attenuation. Okay, the attenuation is nothing but the signal which is going to be get degraded. Here the channel, that is always h of n, channel response we will take it as h of n. Here tau is equal to 0 comma t we are considering, and we will get to a new sample from a Rayleigh distribution for tc, that is the second, and this signal will be interpolated with the autocorrelation function of a of t into delta t. Delta t is nothing but change in time. So now the graphical representation, it is very clear, and how the amplitude is going to be vary at tau is equal to 0, 0 0.5, 1, 1.5, such a way. So this is about the time correlation. Then coming to the frequency correlation, okay, and that is the fading in frequency is that it will happen in the frequency domain, and we will represent it by h of f comma t is equal to 0. Okay, and the new random variable will be the coherence bandwidth, that is bc, in terms of hertz. Values between will be interpolated. Here we can see the details of this, the frequency response. This is the Rayleigh distribution. First signal, how it is converted into the Rayleigh distribution, and what about the coherence bandwidth, that bc is equal to 1 divided by 5 into tau in terms of root mean square value. Then the dispersion, selectivity, duality. Here selectivity and dispersion are the two different effects. So selectivity is nothing but the signal's received value is changed by the channel over the time or over the frequency. But what do you mean by dispersion? That is nothing but the channel is spread out over the time or frequency. Okay, so there is two difference. That is signal received value is going to be changed in the over the time or the frequency domain, and in the dispersion, in the sense the channel is spread out over time or the frequency. So now coming to here, multidimensional correlation. Okay, the signals are, we are all aware about that the signals will be correlated in time, frequency and spatial domains, right? But if you come to the broadband wireless data system, that too in the case of mobility and multiple antenna, there are three types of fading which play a significant role. That is the concept of double selective, that is OFDM, orthogonal frequency division multiplexing. Here long multipath channel is also coming into the account, that is compact with the intersymbol interference and the small coherence bandwidth. So by this, I hope everyone understand about the statistical channel model, that is broadband wireless channel. Thank you.